Okay, so in this class, the quiz is Wednesday. Did I start this? Quiz 1 is Wednesday. And I know some of you are also in dynamics. So that was supposed to be Friday, got pushed back to Monday, got pushed back to today. Then we didn't have class today. So the dynamics test, the quiz, is also going to be on Wednesday. But it should be easy now. You've studied for it twice. Anybody have any homework questions? Yeah. Yeah. No. Okay. So on a given face, let me see if I can convey this. The elements of stress on that face itself is the traction vector. Okay. So each face has 3 elements of stress acting on it, and those are the components of the traction vector. So, like if you had oh, okay, so this represents sigma xx. This represents sigma xz, and this is sigma xy. Okay. And all together, those components add up to give you the traction vector on that face. Okay. But the normal stress is only sigma xx. It's only the component perpendicular. Any other questions? All right. So we've been talking about stress. Now we're going to talk about strain. Okay, so strain. So remember I said that stress is a measure of the local loading at a point. And I guess it's really just the internal loading. That's probably worth writing here. Strain measures the local deformation at a point. I guess that's sort of independent of what's causing it, like the material either deforms or it doesn't. But stress, you sort of have to differentiate, like, are we talking about something applying forces to it or the thing applying forces to itself? So we're talking about internal. And in this class, although not in general, this is the most common way to treat it, but it's not like a universal law or anything. So not generally. Stress and strain have a linear relationship. You know, the two lamest laws in all of physics and engineering are Ohm's law and Hooke's law. Like, give me a break. Like, how little do you have to do to get your name on something? Neither of them say that stuff behaves according to that. They just say, like, if you can find a material that is that follows Ohm's law or follows Hooke's law, then it follows this law. Like, you get to do that however you want. Bullshit. Okay, but if you find a material where deformation and loading have a linear relationship, then you say they obey Hooke's law, right? That's what a spring relationship is. You compare the deformation to the loading, and they have a constant of proportionality. Okay, it's not true in general, but it's true for more or less true for metal springs and stuff like that. Um, so that's called a Hookean relationship. Or if a material has that relationship through its whole range of values or for a big range of values, big range of deformations and loads, then sometimes you hear people call something a Hookean material. Engineering materials, maybe totally generally speaking, have a Hookean relationship for a while, and then when the deformations get too big, they stop having that relationship. But so what Hooke's law looks like for a spring is F equals kx. F is the loading, x is the deformation. For stress strain, it's going to look like this. Voigt strain, that's strain listed as a, given as a list of 6 values, is equal to a big matrix called the compliance times the Voigt form of the stress. So this is the Voigt strain, that's 6 by 1, like a column vector, but with 6 values. Same thing with this Voigt stress, that's also 6 by 1. And the matrix you need to go from 6 by 1 to 6 by 1 is the 6 by 6. So it's a 6 by 6 matrix of constant values. Yeah. All right, so this relationship, just like this doesn't hold for every kind of material, it doesn't hold for rubber or whatever. This relationship doesn't hold for stress strain for everything, but it will for everything we talk about in this class. One other thing to keep in mind. So I think it's a good idea. Try to remind yourself of this every time you see strain values. Ask yourself, is this in a range of reasonable values? Okay. The conditions that we'll investigate in this class require small deformations. The main reason that they require small deformations is because if you take a steel bar and and I'll tell you what's small, like I'll give you sort of a rule of thumb in a second. But if you take a steel bar and bend it past what I'm going to call small deformations, or stretch it or whatever, you move out of the range where that material has this linear relationship, and then we can't do calculations with it anyways. So realistic strain value, that's stress. This is strain. Realistic strain values for our methods are less than about 1 times 10 to the minus 4. Okay. So as we're learning how to do strain calculations and stuff, I'll give you some examples where you get values way bigger than that. But just remind yourself, when in that case and in every other case, when you see values considerably bigger than 1 times 10 to the minus 4, that should just put up sort of a red flag. Okay, so generally, a deformation takes an initial stress cube So think of this thing as being like an infinitesimal cube. We'll start out with all the lengths being the same. And it'll turn it into parallelepiped. And that means that every side is a parallelogram. So that same stress cube turns into this shape after it's deformed. And we'll break up that deformation into 2 different types of deformations. The first one is the lengths of the sides can change. And that is the length changes are what we're going to call the normal strains. And second, the angles change. Let's say angles between faces. Or I guess really it's angles between edges change. And what would you guess those are going to be called? So we have, with stresses, what were the 2 types of stresses? Yeah, normal and shear. We have normal strains. We also have shear strains. And the shear strains are what cause the angles to change. Okay, so you can see like the idea is this, the length of this side got shorter, the length of this side got longer, this angle became more acute, this angle became more obtuse, and all of those are going to be represented as strain values. Yep. Yeah, that's a great question. Well, the stress, there are reasons for, so stress has physical properties that allow us to call it a mathematical tensor. And I'll talk about that a little more later, but not too much, sort of like, um, but it's related to how the values change as you go from one coordinate system to another one. The same way a vector, um, um, a vector actually has to have a certain relationship with rotation matrices to be a vector. Not any list of 3 values is a vector. A vector is a very specific set of measurements, a type of measurements where if you apply a rotation matrix, it changes in a certain way. Okay. A tensor is a 3 by 3 thing, or a 2-dimensional thing, anyways. That also has a relationship with a rotation matrix. And so, yeah, I'll talk about that a little more. But the thing is, strain is not a tensor. Some kinds of strain are, but not the kind we're doing in this class. And so we won't ever look at strain in a 3 by 3 format, because the only reason you do that is to do tensor calculations, and strain isn't a tensor. So with stress, we'll have the tensor, and then separately we'll have the Voigt strain, and they'll both be Voigt stress, sorry, and they'll both be useful at certain times. With the strain, we only have the Voigt strain. So let's start with normal strains. And let's say we start out with a material. We'll start out with a cube, and we'll say that the lengths of each edge are capital L sub 0. And I'm going to think of the coordinate system like this. So the z-axis would be coming right out of the page. And then this deformation happens. This is a very extreme deformation. 1,000 times or something more deformation than we can deal with in this class. Yes? What I'm doing right now isn't a free body diagram, so I would do those separately. And so I'm just trying to illustrate, what make it clear visually that what we have is a sheet that starts out as a square. It has some depth into the page too, but for us, it's this cross section is a square. And then you can imagine if you squish it down like this, it would get, this dimension would get shorter, this dimension would get longer. Not equally, but it does have to do that a little, and that's one of the big effects that we'll talk about. And actually, so we're talking about engineering materials, and engineering materials are always going to have, if you squish it, it bulges. If you stretch it, it's smear. It's called Poisson's effect. Cork does not have a Poisson's effect. Well, it's not really an engineering material, so you don't really use this approach to it. But cork has unusual property that if you take a shape like this and squish it, it doesn't get any wider. And can you imagine why that would be a really useful feature for something that you're going to hammer into the top of a glass bottle? So apparently that's why you use corks in wine bottles. If you do that with steel, it would just break the glass open, you know. Okay, so after the deformation, let's call this length Lx, lowercase lx, and this is lowercase ly. And then to define the normal strains, epsilon xx, I usually call it exx because it has fewer syllables, but that's epsilon, is equal to the, like, after deformation length in x minus the initial divided by the initial. And by the way, sometimes we'll call this deformed length minus initial length delta. So you can also call this delta x over L sub 0. Sigma yy, the y normal strain is the quantity Ly minus L0 over L0, or delta y over L0. And then sigma zz, not sigma, epsilon zz is Lz minus L0 divided by L0, or delta z over L0. Okay, so, well, let's do an example. So let's say that you have a material that starts out as 0.008 meters and a length of 0.01 meters. So, okay, I noticed that as I did that. That's a good question. It doesn't have to. So I could have called this Lx, big Lx, and L, big Ly, and then this would have been Lx minus big Lx over Lx. The idea is it's just deformed minus initial over initial. And then it ends up oh, I didn't give the, whoops. Let's see. So now let's say that this becomes 0.011 meters, and this becomes 0.007 meters. So first, what are, and I'll use a coordinate system like this. What are epsilon xx and yy? And second is this within our range of expected strain values. it doesn't look like that. It doesn't look like that big a deformation. Okay, so sigma xx is the deformed x length, so 0.011 minus the initial x length, 0.01, divided by the initial. And so that's 1, 2, 3. So 1 times 10 to the minus third over 1 times 10 to the minus second. And so we get 0.1. And so even though that doesn't look like a very big deformation, that's, you know, over 100 times bigger than a deformation that would be reasonable for steel if you still expect to have linear stress strain behavior. What are the units? I sort of glossed over that here. Right, strain is unitless. You're dividing a length by a length. And sigma yy, so it's the deformed value, 0.007, minus the initial value, 0.008, divided by the initial value. And so you get negative 1 times 10 to the minus third divided by 0.008. Can someone divide that for me? So negative 0.125. Well, I should have been able to come up with that. Units. Still same definition, so it's still unitless. So then for part B, these are way too big to expect the material to, first of all, to be elastic at all. What does elastic mean? Yeah, so elastic doesn't, so I think when you first, you know, get elastic sewed on your shirt or whatever, you think like elastic means stretchy, but it's not the stretchiness, it's the fact that when you let go, it goes back to how it was originally. So material is elastic if, you know, a material is going to deform when you load it. Even diamond deforms a little when you apply forces to it. But when you take those forces off, it goes right back to its original size. So that's an elastic material. If you deformed a piece of steel this much, you could do it, and it probably would not come in two pieces, you know. But when you let go of it, it would stay deformed. It would be a plastic deformation. Yep. Nope, we're not really. So for people taking mechanical engineering and civil engineering, I think sometime pretty soon you'll have to take material science, and then you'll talk about that there. Retain a linear stress strain behavior. And what we notice here is that strain is less. So whether you're doing your calculations in SI units or imperial units or whatever, they'll be the same. And now shear strain. So shear strain is a change in the angle between edges. And so if you start out with, again, we'll use a coordinate system like this and start out with something that's a quadrilateral. So all of these angles are 90 degrees to start with, and then you deform this material and you get something like this, a parallelogram. So now we'll have these two angles be the same, and these two angles be the same. And let's see, this angle here, we're going to call theta xy. Okay, that red angle in the top right. And in general, theta for AB is the deformed, so after the deformation, it's the deformed angle between the positive A and B faces. So if you think of this as a stress cube, then this is the positive X face, right? This is the, and you can't see the face, I mean, that's the edge that connects to it. This back here would be the positive Y face, okay? And so the angle between the positive X face and the positive Y face is this one. It's always going to start out at 90 degrees. And so over here, the angle that we're going to call theta xy is the angle between this face and this face. Okay. You could do it with the negatives too. It would always be the same angle. But the key thing is if you said, okay, well, this is the X face, this is the negative Y face, I'm going to measure this angle, then you get the complementary angle and everything's backwards. Okay. So remember that it has to be the positive faces that you're measuring. Then these shear strains, and those are gammas, right? Gammas, I think. Gamma xy. Oh, got to do this in radians. Okay, so gamma xy is equal to pi over 2 minus theta xy. And gamma xz is pi over 2 minus theta xz. And all these definitions stay the same. So gamma yz is pi over 2 minus theta yz. So notice if the angle between positive faces becomes acute, is that going to be a positive strain or a negative strain based on those definitions? Positive. One more guess. Positive. Um, so because if this angle becomes more acute, then that angle gets smaller than pi over 2. So you have pi over 2 minus whatever, pi over 3, you get a positive value. If it becomes more obtuse, you get negative values. So physically, that's what these mean. If you get a positive shear strain, it means the positive faces are narrowing their angle. Okay. And if the angle between the positive faces becomes obtuse, then it's a negative value. And again, we saw that the normal strains came out to be unitless. Angles and radians are also unitless, and so that, the same units hold here too. Okay, let's do an example. So I'm going to use a funky coordinate system for this one. Let's say we're looking at this thing. The z face goes this way, and the x face goes this way. And a piece of material that starts out like this with all right angles deforms into a shape like this, and I'm exaggerating it, like, and also these values are bigger than they should be, but you would never be able to see a giant deformation like this with an engineering material. And so let's say that this angle is 1.4 radians. Okay, so that's the same as this angle. That looks like an acute angle. As a decimal, what's a 90-degree angle in radians? Pi is 3.14, so pi over 2 is 1.57. So that's smaller than 90 degrees. And let's say that all angles that we can't see are unchanged. We want to know, what are the shear strains? Well, all we can see is the XZ plane. So we know that there's no angle change in the XY plane or in the YZ plane. So sigma XY is equal to sigma YZ is equal to 0. So the only one we have to deal with is the XZ plane. And now sigma XZ is equal to pi over 2 minus the angle between the positive faces. Okay, so we have to look at this picture and figure out what's the angle that matters to us. We're given this angle, so your first thought is to use that, but that's the positive x face and the negative z face. So we don't want to use that one. We want to use this one. Okay. And so how do we figure out that angle? Ooh, I said they're complementary. I think they're supplementary. I don't know. It's been a long time since I've taken the SAT. Just, yeah, you can just do pi minus 1.43. Yep, that's exactly the right idea. So, the angle we want, whoops. The angle we want is this angle. And so theta xz is equal to pi minus 1.43. So what's that? So 1.71 radians. And so the strain is pi over 2 minus 1.71. And what's that? Negative 0.28. That angle got more obtuse, and that's why we had a negative value for the shear strain. Is that a reasonable value for an engineering material in the linear elastic range? No, not anywhere close to it. There are materials that can strain that much without breaking into pieces. You know, like silly putty or something has no problem deforming that much, but it also doesn't lend itself very well to a mathematical calculation like this. It never has a linear stress strain relationship. So that gets you into all these other problems. Also, it's plastic if you do it. Like if you do a slow deformation of silly putty, it doesn't spring back hardly at all. Is what? Let's see. I'm trying to think. I don't know if I've ever seen a glob of polyester. I imagine that I would imagine that that's a non-linear material and would be hard to calculate because usually large chemical compounds like that have nonlinear behavior. The funny thing is, well, I mean, it's sort of interesting. A lot of materials behave differently depending on how quickly or slowly the load is applied. Try this if you next time you get a hold of silly putty. It's the craziest thing. Silly putty is actually a super brittle material if you load it at a really fast rate. If you take a blob of silly putty and put on goggles and whack it with a sledgehammer, jagged shards go everywhere. And you go around the room and they look like pieces of glass the way they're all jagged and there's just a million of them everywhere. But you go feel it, it's silly putty, you know. And so a lot of times how you treat a material just depends on what kind of application you're going to use it in. Okay. So now that we've defined all these different strain values, we're going to represent the strain. I'm going to call it epsilon sub v for Voigt. And we're just going to list it as in the same order that we defined the Voigt stress. So we're going to do the three normal stresses. Well, these are strains now. The three normal strains in the order you would expect if you had to guess, followed by the three shear strains in the opposite order you would expect. Epsilon XX, epsilon YY, epsilon ZZ. Like no one would ever choose a different order than that. And then gamma YZ, gamma XZ, gamma XY. So notice that that's the same order as the Voigt stress. Next, what we're going to see, and I'm not going to do this at all, but we're going to talk about the relationship the Voigt stress and the Voigt strain. And that relationship is that the Voigt strain is equal to a 6x6 matrix times the Voigt stress So this is a 6x6 compliance matrix. And that means that this is going to have small values, very small actually, smaller than the strain values. And we also have the relationship, I'm not going to write out the values this time, but the Voigt stress is equal to a 6x6 stiffness matrix times the Voigt strain. And the compliance matrix is the inverse of the stiffness matrix. And the stiffness matrix, is the inverse of the compliance matrix. Okay, so that means that the stiffness matrix has big values, huge values, bigger than the stress values. Okay, so if we figure out what these 6x6 is 36 elements, right? So if we figure out these 36 values that represent a material, then we can go back and forth. All we have to do is measure the deformation and we can calculate the stresses, or measure the stresses and we can calculate the strains. And that's a lot of computing power, you know. But then you're like 36 values, like we're going to do 36 individual material tests to figure out these values. Like that sounds like a nightmare. And it would be, except in a lot of cases, this reduces down so that all of these values are determined based on just two constants. And those two constants come from really easy material tests. So that's what we'll get to next time. Yes? Uh,